Welcome to the FDP and recent trends in power electronics, day 4. Today we have a esteemed speaker, Dr. Moumita Das. She will talk about power electronics things to power trains actually. So before going to start the session, I like to introduce her to all the participants. Dr. Moumita Das is a senior member of IEEE. She has received PhD degree from the Department of Electrical Engineering at IIT Bombay, India. After completion of PhD degree, she has done postdoctoral research in the School of Electrical and Electronics Engineering, University of Manchester, UK, and in Department of Electronics Design, Mid Sweden University, Sweden. Currently, she is an assistant professor at Indian Institute of Technology, Mandi, India. Her research interest includes converter topologies, modeling design, and control with a focus on renewable energy sources and electric vehicles applications. Storage technology, wide gap, band gap device applications, designing high frequency magnets. So with the introduction, I'd like to hand over to the session to Dr. Moumita Das. Ma'am, please start the talk.
Okay, thank you very much for a nice introduction. So I'll start my presentation. So what I will do, so there are actually different parts in my presentation. So after every completion of every part, so if any of you is having any question, then you can ask me. Then at the end, again, like you can ask overall questions on the presentation. Is it okay?
Yeah, fine, ma'am, fine.
Okay, thank you very
Even
much.
they like to put it in chat box also, ma'am, if they have any issue. I will read it.
So yeah, sure,
Yeah.
that
I will
would be
read.
good.
I'll read it for you, ma'am. Yeah.
Sure, thank you very much. So I'll share my screen. So my screen is visible to you. Can you see my screen?
Yes,
Hello?
yes, ma'am.
Okay.
Yes, yes.
Thank you. So today I'll talk about high-speed railway traction applications. So basically, so this talk consists of different parts. So one first is the introduction. So what is the requirement of high-speed traction? And then different locomotives, so whatever like we are using currently in trains, so based on the power electronics converters, so how the structure looks like, and what we mean by high speed traction, so that I'll discuss. And then power converter, various power converters which are basically used in traction applications, how they look like and what are their ratings, device ratings. And then I'll start wide bandgap device related talk. So basically, what is the importance of wide bandgap device in trains, and how this wide bandgap device era is changing the application of power converters, specifically for traction applications. And then advantages of using wide bandgap devices, and how the power converter will be using wide bandgap devices for traction, that I'll discuss. So the introduction consists of like, what is the electric traction? So traction, probably you have heard of, like any process of moving vehicle, that is non traction. So if we are using electric power, so then that will call electric traction. So now you have probably seen that electric traction relate for train application, metro or tram, anywhere wherever the electric power is used. So earlier, actually, you must have heard of like generator, diesel generator based train. So those are like kind of the application where electric power was not used. So but like the trains where electric power we take from the overhead line, and that is then processed for application for running of the train, so that then it will call electric traction. So why electric traction system, that I'll show you, that what is the need for that, and what are the different advantages of using electric traction. Then nowadays, I mean, if you see the power converter application, so everywhere actually people are trying to go for high frequency operation, so that will help in many ways that I will discuss in details. when I'll discuss about wide bandgap devices. So, and then how that is actually helping in train applications. So, having said that, so one of the important factor is the reliability and safety. So although like we are going for high frequency operation, so how reliable the systems are they safe, or is the technology mature enough so that we can use it for any application? So now this train, if we see that like nowadays probably you are hearing that many things about high speed trains in India, so it is there in many other countries. So Shinkansen, basically that is high speed train, so which was first developed in basically in Japan in 1964, which had the maximum speed of 210 kilometer per hour. So so that was actually they developed that in 1964. So now how this system basically was developed there, and then how we can actually use power electronics converter in order to achieve that kilometer range, or maybe more than that. So that we will see eventually. So the traction system, if you see the traction system, so there are actually various types of electric traction: DC traction, AC traction, multi system. So what are this DC, AC, multi system traction? That let's see that how this structure looks like. So basically DC traction means, so the idea is that that is also electric traction, but we basically in the train, so DC power is taken. So how this DC power is taken? So if you see my screen, there is one block diagram I kept. So here from the overhead line, so overhead line it is AC. So from there in substation, so that AC is converted into DC, and which then is used in the train. So if you see in the dotted box here, so this box is having converter. So that box can contain transformer plus converter, or like converter structure which may have transformer in between, like high frequency transformer. So in the substation, then what it is doing, so it is converting AC to DC. And this DC basically, then what is happening, the train that catenary is through catenary, so it is actually going into the train. So DC power is the going into the train, so that is known as DC traction. So now if you see the AC locomotive, so AC locomotive, how it looks like, so basically from AC, so like from overhead line directly AC is going into the system, basically in the train. And then there the AC input is processed. So basically there different converter structure is there, so that AC can be converted into DC, DC to again AC, which goes to motor. So depending upon the type of motor is used, so then that power will be transferred to the motor, and then which will help for movement of the train. So that is AC locomotive. And what is multi system? So basically what happens in multi system, there the combination of AC and DC will be there. So in some part of the system, so then what will happen for like traveling some distance, it may happen that power is taken from the DC source, and for some distance power is taken from the AC source. So that generally what happens, the process is can be implemented by changing the basically the basic converter whatever is there in the train. So by changing that structure, or maybe there will be dual systems, so where AC and DC can be used both, like depending upon the kind of availability, and also like kind of way it is actually implemented. So if you see here, so in this particular block, so which is given in AC configuration, so there actually two different connections are given. One is for AC, another is for DC. So similarly, like the converter structure will also be very different. So there AC and DC both can be taken. So now as you can see, this AC, DC, all these things, so how it is taken? So basically what are the voltages from here, like these sources are taken? So basically what happens when this AC, uh, so if you see in this AC locomotive, so the overhead where which is given here, so that is either like 15 kilovolts and then a few hertz, or maybe 25 kilovolt and 50 hertz. So that is the range of the voltage from here the source, the basically connection is taken for the converter. So I'll show you details of the converter. So then this voltage is actually processed in order to provide to the motor. So now the traction transformer. So these are the like different systems. So basically overall system for railway application. So the important parameter which is there in the system, whether it is DC system, DC traction, AC traction, all the multi system. So the important parameter is traction. So sorry, transformer. So there are different types of transformer. One is LFT, low frequency means line frequency transformer. So whatever the frequency is given in the line, so basically the overhead line which is shown here. So that is if it is 50 hertz, 50 hertz. If it is like 16.7 hertz, 16.77 hertz. So that is the frequency is considered for the transformer. So that transformer is known as the low frequency or line frequency transformer. And another is the power electronics transformer. So power electronics transformer is basically where the transformer is placed in between the converter, and the converter can operate at high frequency. Depending on that, the transformer will be high frequency in nature. So then a power electronics transformer can also be known as a medium frequency transformer. So it can operate from like few tens of hertz to few hundreds kilohertz. So that is like a medium frequency transformer. So the rating of the transformer, it is like it will have 20,000 kVA. The frequency it can take from the like input, it can be 50 hertz, 25 kilovolt, or it can be 15 kilovolt and 16.7 hertz. And then power factor preferred is 0.9, and zero load condition it will be around 27 kilovolt. So basically the input voltage, so that will be 27 kilovolt. So now what is like difference between this power electronics transformer and the line frequency transformer? So as I said, the line frequency transformer, it should be able to take this 15 kilovolt 16.7 hertz or 25 kilovolt 50 hertz, which are generally used for railway catenary systems. And the power electronics transformer, so basically it operates like medium frequency. So like earlier the concept was like medium frequency, basically from hundreds to tens kilohertz. So that is known as medium frequency transformer. But now the trend is changing due to the development of wide bandgap devices. So people can think of high frequency transformer. So that is why like in the power electronics transformer, both medium frequency and high frequency transformer can come. So this can take line frequency of 50 or 60 hertz. So since the transformer can operate at medium frequency, but the front end and the output power electronics converters are important in this case, because like in order to process that power, like if we are considering like tens of kilohertz, let's say 50 kilohertz. So then the power electronics converter switches are required in order to process that power in that frequency range. So that is why here uh, it is very much important. But in line frequency transformer, it is not that important to have like power electronics converters. Okay. So the front end converter, so basically it will be connected directly to the catenary. So from the overhead line, whatever is coming in the train, so that will be connected to the front end converter. Since the voltage level, you can see here the voltage levels are 15 kilovolts and 25 kilovolts. So then what is happening, if there is power electronics converter which is connected, so basically the input which is having let's say 25 kilovolt in that range, so then converter switches need to have that much capability. So what happens, like whenever we are connecting any converter, so if the switch voltage is coming this much, then switch should be able to withstand that much voltage. If the converter is like very simple, like H bridge kind of converter, then what will happen, that voltage rating of the switches need to be this much. Or if the switches cannot withstand this much voltage, then probably we need converter topology, which can be like multiple converter can be connected in series cascaded manner, so that each switch may not require this much voltage, so it can be divided between like different cascaded branch. So depending upon the number of cascaded branch, so let's say if 10 cascaded branches are there, so then each cascaded branch will have 2.5 kilovolt at the input. So that way voltage rating of the switch will reduce. So that way the converter configuration will play a very important role in this power electronics transformer part. So then another important thing is that due to limited switching frequency of high voltage power devices, the terminal voltage usually are pulsed but not sinusoidal. So then, if it is pulsed, so then it will affect the power factor. So then we have to see that how to improve the power quality. So if the power factor is getting affected, if the terminal voltage, if it is pulsed, if it is not sinusoidal, so then we have to see that what is the switching frequency. If the switching frequency is very low, so then what will happen, that may cause low power factor. If low power factor, so then there will be harmonics, power quality issues, there will be lots other problems. So we have to see that how we can tackle those kind of problem in power electronics transformer. So basically the advantages of using power electronics transformer over low frequency transformer is that size and volume will reduce. As we go for high frequency operation, you all know that the size of the magnetics will reduce down. So then obviously that is like that will reduce the cost of the system. So that is like very big advantage in any power electronic system. So then efficiency will also improve. So if the volume if volume reduces, so then the parasitics associated with the system, so that will reduce, then that will increase the efficiency. Then the quality of the power, so basically if we can operate at very high frequency, then what will happen, then we may get better power quality, power factor will improve, harmonics and all this harmonics will reduce, and transient performances will be better. And then additional functions such as the power flow control, basically what happens in the power systems, so whatever problem related to voltage sag, swell, or flicker compensation, so those kind of things can be improved by using power electronics converters. But the disadvantages, what are so we cannot have all the advantages, so there will be definitely some disadvantages. So what are the disadvantages? So basically what happens, we need to connect high voltage converter at the input. So that is actually very big disadvantage, because like then we have to see the converter topology which will be suitable for that. If the we can actually step down the voltage first and then use the converter, that is actually much more advantageous. Then we don't have to think about the converter topologies. Then if we are using many converters in series, then the system cost in that respect will increase. And then if we use like more number of switches, like power electronics converter means like there will be combinations of different switches. So then what will happen, reliability, how that can be maintained in the converter, so that is again questionable thing. And then again, like designing multiple converter will be challenging for the manufacturer. So these are the different pros and cons use of power electronics transformer over the line frequency transformer. So if you see the structure of the AC locomotive, so line frequency transformer, it looks like the, as you see the left side block diagram. So it is actually basically transformer is connected to the AC catenary, and then once the transformer step down the voltage, then it is connected to converter. So basically AC to AC converter here it is shown. So that converter then can be connected to the motor to control the motor parameter. And then if you see the right side block diagram, that is power electronics transformer based railway traction system. So here if you see, there is front end converter. So basically AC to AC converter is connected at the input. So that can be any kind of AC to AC converter. So multiple converter can be connected in cascaded manner. So different converter topologies can be used. So that I will discuss later. So that converter again will convert this line frequency, which is the frequency of this AC catenary, to medium frequency. means like if we are considering that few hundred hertz to few kilohertz, then that will be like medium frequency. So if you see this line frequency, which is basically AC sinusoidal in nature, so that is converted into pulsed kind of signal in medium frequency, which then transferred to the secondary side by using medium frequency transformer, and then this medium frequency signal then processed through the AC to AC converter to supply to the motor. So if you see here, the number of steps are more. So in order to have medium frequency transformer, so the front side there is one block, so for the power electronics converter that is required. So that is the additional thing in the power electronics transformer. So designing this converter will be challenging, and as we try to go for higher frequency operation, so again like designing the overall system will be challenging, but the advantage will be the size, and the size of the overall system will reduce down, and also like efficiency of the system will increase. Here in the left hand side, if you see line frequency transformer, so here the this transformer will be very bulky, and that will also cause like lower efficiencies. But due to the inclusion of power electronics converter, this efficiency and the size, they are the benefit we will get. So more efficient, high efficiency, and the less size. So if you see the power converter structure, so basically what happens, like from the overhead line through pantograph, so it goes to the like main transformer if it is line frequency transformer. So then through rectifier, then it will convert AC to DC. So the DC power goes to the inverter, and which is basically connected to the motor. So basically this DC power goes into the different inverter, and which will be connected to the different motor of the traction, railway traction. So then that way the motor can be controlled through the inverter. So now this medium frequency based traction system, so this is one of the structure for medium frequency traction system. So if you see the diagram, so this I have taken from reference. So all the references I have listed. So whatever I am discussing here, I have taken from different references, and you can refer to those references in order to know more about this kind of system. So if you see here, so here the overhead line, it is of 15 kilovolt and 16.7 hertz. So this system is actually developed in 1985. By one of the university in Austria, Leoben University. So they what they have done, so they have used, so input side, so there is one rectifier, so diode bridge, simple diode bridge rectifier is there. So if you see here, input rectifier, so the advantage of the system is that there is no DC bus capacitor. So this is another important thing, is that in power electronic system, if we use more number of capacitor, then the reliability of the system will reduce. So that is why if it is possible to remove the capacitor from the system by using some converter structure, or some way, if we can reduce that size, so that is much more beneficial. So then the reliability of the system will improve. So here in this case, so they have actually removed this DC bus capacitor, which is generally required after the rectifier. So this is the diode bridge rectifier, which is basically converting this AC, input AC, which is coming from the overhead line to DC. So now this DC, what is then happening? So this is actually matrix converter structure. If you have heard of matrix converter, so this is another multi-level kind of converter. So the different switch combinations are there, so that will help to reduce the harmonics by operating it such a way that the signal will be close to the sinusoidal kind of signal. So then this matrix converter is placed, and then this matrix converter convert this signal, so this DC signal into AC, so which will be processed through this 400 hertz medium frequency transformer. So the medium frequency transformer is placed here. So if you see 400 hertz medium frequency transformer, so that processed AC then again will be converted into DC by using diode bridge rectifier this is output rectifier, here it is placed, and then by through the DC to DC boost converter, that signal, DC signal, will be again like processed by using DC to DC boost converter, which then will pass through one inverter to the motor of the railway traction. So basically here the important thing is that the power is processed by using 400 hertz medium frequency transformer. In order to process that power, in that transformer, the various stages of power electronics converters are used. So if you see here, basically there are actually before inverter there are 4 different stages. So inverter is common for line frequency or medium frequency transformer. So basically line frequency transformer, AC to AC converter is used. So in medium frequency it is DC to AC. So this part will be there, like whatever converter stage is required. So before that 4 different stages are used along with the transformer. So as you can see, there are like multiple stages are used. So again, like implementing this kind of system and then maintaining reliability of this kind of system, it's a challenging job for this power level. So this is another medium frequency transformer. So basically if you see here, so this transformer is developed by this system is developed by Royal Institute of Technology, Sweden, in 1993. So this is matrix front end. So this front end converter is matrix converter, and then output converter is 4 quadrant output converter, also it is matrix converter. Okay, so they both front and the secondary, basically front end and the output converter, those are matrix converter, and then in between medium frequency transformer is placed. So now here in this case, in order to connect this converter, like device rating, if it is not high, so then what is done, so multiple converters are connected in series. So if you see the converter which is placed in, which is shown in A, so that is one converter. So this kind of converter is connected in series, input side converter. So basically if you see the front end converter, it is connected in series in order to get like lower voltages across each branch. And then the secondary side, it is connected basically it can be connected in series or parallel depending upon the requirement. So that here the advantage is that it reduces the current harmonics. So different structure focuses different aspect. So this kind of structure will reduce the current harmonics. So again, like harmonics, if it is reduced, then obviously power quality will be much better. So then this is the simplest structure. So you know about H bridge. So basically so the H bridge is used here. So like different module. So if you see here module 1, so that is one H bridge. Module 2, there is another H bridge. So different H bridges are connected in series, and then along with H bridge there will be like dual act bridge. So which we will be having this medium frequency transformer in this in between this, and that actually converts the power to the output DC, and then through the inverter that will be processed for the motor control. So here the structure suggests that the input side, the cascaded H bridge modules are there, and then high voltage IGBTs are used in this case, and then output side parallel configurations are used. So basically what is happening, because the input voltage is very high, so the series combinations are there at the input side, and then output current requirement is very high, so that is why parallel combinations are used in the output side. So the advantage of this kind of system is that it is having soft switching operation, which will reduce the losses in different IGBTs and then improve the efficiency of the system. So this is developed in 1998. So before that, like whatever structure you have seen in these cases, so those are all like thyristor based system. So in this converter, IGBT is used. So as you know, like there is like huge difference between use of thyristor and IGBT, because you know thyristor cannot operate at very high frequency. Then IGBT came, which allows the converter to operate at higher frequency and higher power level. And MOSFET is there, like which can operate at high frequency, but you know like power level is not very high. So that since the railway traction application we need high power, so that is why IGBTs are used here. Okay, that will enable for the converter to operate at higher frequency. So if you see picture of different power electronics transformer, so basically medium frequency transformers are there. So this medium frequency transformer, if you see, so that is actually this is actually developed in EPFL, Switzerland. So they have shown, so basically this this transformer which is shown in A, so that is 36.3 kVA medium frequency transformer, and in B 400 kilowatt test reach is shown for this railway application. And this dual active bridge which is shown in C, so if you see C, there is structure of dual active bridge, and then the medium frequency transformer which is placed in this dual active bridge, that is shown next to it. And then the D, there is the converter, it is basically a resonant converter. So there is difference between converter which is shown in C and which is shown in D. So the converter in C, since it is like a dual active bridge converter, the operating frequency of this particular converter is much lower than that of the resonant frequency converter. So again, like this comes in the converter part, as you know, like so there is only difference in C and D is that there is one additional C is there in D. So this any resonant converter that actually allows the converter to operate in like much higher frequency. So what will happen, that will have, like if you see in resonant converter, so that will be in details of resonant converter. So that has different region, so which will allow the converter to operate either inductive capacitive region, and then that will have soft switching feature which will allow the like high power converter to operate at high frequency. So that is why nowadays if you see like resonant converter based work, so those are used for high power application because it will allow the switches to operate in soft switching mode. And then the what will happen, the losses will be less, and then requirement of heat sink in the converter which will be much less. That will again reduce the size, and then reliability of the system will increase. So those things, those advantages will be there. So here if you see the transformer structure, so basically from these two it is very difficult to understand, but at least I can tell you the transformer which is used in C, so that is of 10 times of the transformer which is used in D. So due to the frequency operation, so basically in C it is a 1 kilohertz frequency operation, and in D it is 5 kilohertz frequency operation. Okay, so these are all like kind of advantages we will have if we try to go for high frequency. So now if you see the diagram which is given in the right hand side, so basically which is you can see that for locomotive application, so the test rig is developed in like Tsinghua University in China. So they have developed this test rig for this railway traction application. So this is the converter structure which they have used. And so like there are like different like archaeology can be used. So the basically first A, if you see the secondary side, two different converters are there which will be connected to motor, and then B, it is like multiple converters which can be connected in like parallel, which can be used, which can be connected to the motor. So that way like this converter structure can be changed, and then that can be used for this railway traction. So this converter which is given in the input side, if you see, then so CHB means cascaded edge bridge converter. So the edge bridge, as you know, so like four switches with like two switches in each leg which will be connected in parallel. So that way these converters are like shown, and these are used for traction application. So now this is another picture. So basically this is the H bridge converter which is cascaded at the input side, if you see here. So it is the system configuration, and then the laboratory prototype which is developed like for 12 kilowatt 400 volt laboratory model which is shown here. And then this is one matrix converter based power electronics converter, so which is having this multi-winding medium frequency transformer with first one is with joint multi-winding, and here the second one, if you see, the with separate multi-winding. So that way different structure is used, and different structure will have different advantages. Obviously we cannot have all the advantages in one converter, so depending upon the requirement we have to see like which one we need to focus. So depending upon that we can choose the converter structure. So these advantages of power electronics transformer based system, as you know, the size, weight, there will be advantage. Then the cost, I mean, like size, weight, if it reduces, depending upon that cost, and then if the cost will reduce and efficiency will increase, all these advantages will be there. So if you see that, like for like 15 kilovolt 16.7 hertz application, the power electronics transformer based system may have 50% lower system weight and 2 to 4% of system efficiency higher than that of the line frequency transformer. So the in terms of efficiency, that may not look very high, like 2 to 4% only, but like in terms of size, if you see that, it will be half of the weight of the line frequency transformer. So there will have a huge advantage. And then since the power converters are there, different power converters, then we can actually use like suitable converters in order to improve the power quality. So in power systems also, like different converter can be used for like if there is voltage sags, well, and if the fault condition is there. So those kind of thing can be implemented for like this power electronics transformer based system itself, so that it will not affect the traction system. Then one only thing is that there is like this power electronic system, so it is like currently in research level. So still, like there are like many challenges which need to be solved in order to kind of use it for actual railway traction application. These like whatever things, advantages and everything are shown, so mostly those are in research level. So until and unless we solve all the challenges, that cannot be implemented. And so again, like once it is implemented, so then probably we will get to know like what are the real advantages in actual system we may have. So those are the things related to power electronics transformer. And the opportunities in this is that one main opportunity in research as well as you can say in application is that, so since this there are power electronics converters, so now where IGBTs, most of the systems are based on IGBTs. So those IGBTs can replace by wide bandgap devices. So wide bandgap devices, like depending upon the rating of the system, so it can be silicon carbide, gallium nitride. So then what will happen, then the system frequency will be much higher, then there will be many other advantages, and then again many other challenges. So this high voltage if you see this IGBTs, silicon based IGBTs, so those are like the maximum rating around 6.5 kilovolts. The silicon carbide IGBTs, now it is available around 27 kilovolts. So again, the if the voltage level of the devices are higher, then the circuit structure will be much more simpler. Means instead of using different cascaded converter, one single converter can be used in order to process the power. So then like less number of converters will be there, then simple structure will be there, then the reliability and then control will be much easier, implementation of all these things. So I mean, like if less number of a cascaded system is there, then the efficiency and will be much higher, then the system will be smaller. Okay, so those are the related to high voltage power device applications in railway traction. And then high voltage, high power, medium frequency transformer. Again, like at this moment, the transformer which are like kind of used in the traction application, those are like medium frequency. So if we try to increase the frequency further, then what will happen? There will be challenges in order to use those transformer. Like now the high power transformers are mostly like used for lower power high frequency transformers are mostly used for lower power applications, not like railway traction applications. So if we go for high power applications, so then what will happen, different kind of cooling mechanism we need. So it can be oil cooling or any other like insulation of this transformer wire which are used. So that will also be like kind of one of the challenging tasks to look into, like what should be the kind of insulation of the wires for that high frequency operation, high frequency and high power application. And then cooling mechanism, so those are related to the implementation of the transformer. And another important thing is that the losses in the core, so basically losses associated with the transformer, so eddy current loss and proximity effect, all these things. So which basically generally not involved in any high power low line frequency transformer, those will become important. And then we have to see that how these loss distributions are, and how we can actually reduce these losses, or what kind of core is required. So generally what happens in line frequency transformer, silicon steel laminations are used in the core. So if we try to go for high frequency transformer, so these silicon steel laminations are not suitable. So you must have heard of ferrite core. So those are used for a high frequency low power transformer. But like if we try to go for high power transformer, so again like different type of core material need to be investigated. So some core materials such as amorphous and nanocrystalline, these are in use for high power high frequency applications. So those cores need to be investigated for this railway traction application. So and we have to see that what will be the magnetizing effect and leakage inductance effect of this medium frequency transformer. So and we have to see whether implementation of soft switching will be helpful or not. So those kind of things need to be investigated related to the magnetics of this high frequency high power transformers. And then again, like system topologies, right now the topologies mostly used either matrix converter or the cascaded edge bridge. So like the converter which are complex in nature. So if we have high voltage device, so probably we may come up with some simple topology which will be easy to control. So again, like system investigation of system topologies with respect to the device and high frequency transformer, that is also another important area which people can look into. And other issues related to the operating frequency and the number of cascaded module optimization, control, reliability, again like the fault like how we can protect the system from the fault. So all these things, so basically reliability of the system is another important area can be looked into. Again like we have to see the system level converter operation with respect to high voltage high frequency device. We cannot only focus on the component part, we have to see that how these components are operating in this application. So the system level operation can be looked into. So these are the key opportunities in this power electronics transformer based system for railway traction applications. So now the devices, if you see, so in traction, so like whatever converter topology you have seen in till this till, like this much presentation, so those are all silicon devices. So earlier like mostly thyristor based converters are used. Those are having like high switching losses. You probably know like the disadvantages of these thyristors. So basically high switching loss, low switching frequency, high line current harmonics, all these problems will be there. And then it is not fully controlled. So then like IGBTs came up, and then people started using IGBTs. And then what will happen, there are like many advantages of IGBTs, so those are there. But there are some limitation of silicon devices still, till some extent only they may provide that much advantages. So that is why people started looking for different other devices which may have advantages over the silicon devices. So those are known as wide bandgap devices. I'll tell you why those are called wide bandgap devices. So there are like two wide bandgap devices which are available commercially at this moment. So silicon carbide and gallium nitride. So so now if you see, okay, before going to device part, do you have any questions? Maybe we can discuss at this moment, then I can go to device part.
Yeah,
Hello.
any questions for this session? Welcome to ask by the participant.
Okay, if you don't have, then probably you can ask me at the end. If you
Okay,
have,
okay. Yeah.
if you have any questions, then you can ask quickly. Otherwise, you can wait till the end.
Oh, I have one quick question, ma'am.
Yeah, yeah.
Yeah, is there any standards with which you are saying that medium frequency, high frequency, or any power level which suggest? Are there any standards developed yet?
So the thing is that if you see, if the power level for the transformer, that is like power level for the traction, that is fixed. So if I have given here the rating, this is the like capacity of the transformer, basically overall system, so that is fixed. But the medium frequency, when we are saying, so like before the development of wide bandgap devices, basically the using the silicon IGBT, so I have given here it is from like hundreds to tens of kilohertz. So that is known as medium frequency, and like in literature, that is only given as medium frequency transformer. So generally if you see the converter structure, so they are mostly, it is used like around 400 kilohertz. So if you see here, so the 400, sorry, not kilohertz, 400 hertz. So 400 hertz, so that is actually considered to be medium frequency, because now the system can operate in megahertz, so that can be considered as high frequency, like it can operate. So this is 400 hertz, and then I have shown one transformer here. So if you see here, this transformer, these two transformers are shown here. So these are also from literature. So one transformer can operate at 1 kilohertz, another in 5 kilohertz. So those are comes under medium frequency. So few tens of kilohertz, it is considered as medium frequency transformer. So high, if you see in literature, there like for railway traction operation, this high frequency is not yet used. This term is not yet used. Line frequency and medium frequency transformers. Since this medium frequency transformers comes under the power electronics transformer. Hello.
Yeah, ma'am. So, is there any development of this medium frequency transformer in India in any of the institute? Have they developed? Or
I
because these are from the outer institute outside
Yes, yes.
India.
Yes, yes. This for railway application, as per my knowledge, I don't know anywhere like they're developing this in this power level in India. So in outside, there are like lab prototype for this much. So again, like it is as per my knowledge. Yeah.
Okay. So, what do you think can be the main challenge for going to the medium or high frequency transformer?
So the thing is that if you consider high frequency transformer, again, like there will be challenges, like the converter which will be operating at that frequency, the switches need to operate at that frequency, so that the power will be processed. So now this wide bandgap device era came, so then there are switches which will be suitable to operate at that power level, at that frequency, high frequency. So that was one of the challenges, like high power and high frequency you don't get to see in silicon devices. So IGBTs have they are having limitation. So now I have shown here, so like in terms of like limitation of high power high frequency transformer. So those, like one of the important limitation is that obviously the device part will come first, because converter has to operate at that frequency level, and then with respect to the magnetics, the insulation, whatever you are using for the winding of the transformer, that is one important thing. And then the cooling mechanism, cooling is another important thing. So which will be challenging to like implement for this high power high frequency transformer. So till now those are kind of limited for low power high frequency transformer. But like high power transformer, what will be the challenges? So that can be like whoever will be working in that area, they can look into that part. And also the losses, like how this AD current and proximity effect. So we have the idea about those losses in lower frequency level, but like in higher frequency level, how this loss distribution will be, those need to be investigated. So those will again like will be under the like whoever looking into the magnetics part, so they can explore in that area. Another important thing is the core material. So core material mostly you I mean here at least in India it is very easy to get ferrite core. Obviously silicon steel lamination for line frequency it is there, but like high frequency mostly ferrite cores are used. But for amorphous and nanocrystalline, again like we have to like import it from outside. And again like we really don't have any like industry, so they can actually provide these things very easily. So even for lower power application, so that is also important thing. So there are like three different challenges: cooling mechanism, then the loss distribution, how it will be in high frequency high power, and the core. So then probably we have to go for different material which will be suitable for high frequency. So when we moved from silicon steel lamination to ferrite, so that was because the like development of IGBT, it was it was suitable to operate in like a kilohertz level, like few range of kilohertz, so in that level. So that is why people started using a ferrite core. Now again like different other material, nanocrystalline, this kind of material. Yeah. So is it clear?
Yes, ma'am. Yes, ma'am. Thank you, ma'am.
Okay. Any other questions? Okay, then. So then I'll discuss a little bit about the wide bandgap devices. So basically, wide bandgap devices. You can see my screen, right? Hello.
Yes, ma'am. Yes, ma'am.
Yes, yes.
Okay. So you have probably heard of these wide bandgap devices. So there are actually different wide bandgap devices. So you have probably heard of silicon carbide, gallium nitride. These two devices, these are commercially available devices, but there are other wide bandgap devices which are in research level, which are not commercially available. So next device which like people are expecting to be commercially available is the diamond device. So like as you see so there are like there are other devices also, those will take some time to come commercially. But like after silicon carbide, that there is like gallium nitride and then diamond. So these are like kind of expectation that people will get diamond device. So what is this wide bandgap devices? So if you see the band gap, so again like it will go into electronics. So basically the band gap in silicon carbide, gallium nitride, diamond, it is very different. So in silicon carbide it is around like 3.2, in gallium nitride 3.4. So if you see from this structure, so it is given. So basically silicon, so what is the band gap of the silicon? So it is like near, if you see from this diagram, it is around 1. And then if you see silicon carbide and gallium nitride, so like silicon carbide is around 3.2, and then gallium nitride 3.4, and then diamond it is expected like it will be around 5.5. So that way it is actually defined as the wide band gap, because the band gap is much more higher than that of the silicon device. So now how these devices will help us, means if there is like wide band gap, so how this will help us? So basically this will enable, one part is the high voltage operation. So as I told you earlier, so basically IGBTs, if it can like till now like whatever is used, so that is suitable to operate 6.5 kilovolt, and silicon carbide which is now available for like 27 kilovolt in that level. So you can understand that it is like much higher voltage than that of the silicon device. So it will enable us to operate in high voltage. So that is one part. And another important thing is that if you see the electron velocity, so with respect to silicon, so silicon is shown in yellow, and blue and red are for this silicon carbide and gallium nitride. So electron velocity is much higher than that of the silicon. So then that will enable high frequency operation. So again like with respect to silicon, there will be much higher frequency operation. And then if you see the thermal conductivity, so thermal conductivity is also shown here. So then it will enable high temperature operation. So basically there are three properties which this kind of devices, because of this kind of device means the material, basically this is depending upon the material people have used. So they have investigated, they did research in this area, and then they came up with the solution. Okay, these materials will have these advantages, and this we can use for device application. So that is why the silicon carbide and gallium nitride, they will have advantages of high voltage, high frequency, and high temperature. So these three properties we will get from this wide bandgap devices. So now if we get these properties, so then what will happen? So basically what are the advantages will be there? So then if you see here applications, so high power applications, you can see here that there are two different applications are shown. In blue, high speed application; in green, high power application. And the silicon, if you see here, it is actually shown in the orange envelope. So that is for silicon. So that is the maximum capability of silicon. So operating frequency in silicon, if you see here, so it is shown maximum around, let's say, few hundreds of kilohertz, and then the power level, if you see here, that few hundreds of kilo volt ampere. So this is the maximum capability of silicon. Again, like I mean, there are like important factor is that if the device, so from this envelope, if you try to see, if the device is having higher power, so that is suitable I mean, this kind of device is suitable to operate at lower frequency, and if it is having low frequency, then it will be suitable to operate at higher power, and high frequency that will have low power. So these are the kind of properties devices are having. So now due to the development of this GAN device, so if you see this GAN device, it is more suitable to operate at high frequency rather than high power. Obviously high power means with respect to these devices, if you see the high power level of the power is almost equivalent to the silicon, but a silicon carbide device, it is suitable to operate much higher power. So if you see the green envelope, so it can operate in MVA level, like few tens of MVA level, so using silicon carbide device. And the frequency level again will be like kind of maximum frequency will be equivalent to silicon device, but GAN, which can operate in megahertz, like few tens of megahertz application. So different applications are also shown, like which are very popular in this by using these devices. So GAN are like low power kind of application, basically server applications. So this is different type of converter which are of low power and nature. And then for electric vehicle, like the low power converters which are placed. And then silicon carbide are basically used for higher applications. So if you see one application which is shown here, railway, then wind turbine, then central inverter, and then like industrial application, any industrial application, those kind of applications where applications silicon carbide are used. So basically wherever the high power comes, so there silicon carbide is used. One disadvantage with respect to GAN is that it is not suitable to operate that kind of frequency level. With respect to relative to GAN, it is lower frequency device, but it is like kind of suitable to operate few hundreds of kilohertz. So that way it is high frequency device. So now, so why this wide bandgap devices came? So if you see here, so this devices, so like progress in the power electronics, basically power electronics field, it is started due to the development of the device, so power semiconductor device. So when this SCR was invented in 1957, in that time the new area started, that is power electronics. So without device like power, there is nothing in power electronics area, right? So since now there is like kind of saturation in the like whatever benefits we get from this devices, from this application of the devices, so then people started looking for new devices, so that is which can enable new like area, like not new area, basically there will be advantages in this kind of area. So that is why the people started looking for new devices, and then they came up with this silicon carbide, gallium nitride, which are commercially available. Then next some other devices will come, then they may have other advantages, other challenges will be involved. So these, whatever I'm saying, those are the advantages. There are like lots of challenges using these devices. These devices are new. Like till now, only silicon devices were there. We know how these devices work. What are the challenges of operating these devices, and like how to tackle those challenges, and manpower, whatever we have now. So they are trained in using these silicon devices. But like in order to use these devices again, like new knowledge is required. So new challenges need to be solved for like now this mostly like in research level and few application side these silicon carbide devices are used. So people are still trying to see that how these challenges can be tackled, how these devices can be used in applications. So this power electronics advancement, if you see here, so here the left hand side, which is like basically below this blue line. So this is the limit of the silicon device. Above the blue line, where the limit of the silicon device start, from there the wide bandgap semiconductor devices started. And then if you see here that like depending upon the frequency and the power level, if you see here, so the HVDC power distribution is having like maximum power like volt ampere rating, so which is having like much lower frequency operation like that in that range. And then if you see that this microwave oven, that is having like much higher frequency, the power level is again like much lower in that case. So everything, whatever application placed in this line, so those all can be implemented using this wide bandgap devices. So now, having said that, silicon carbide device is most suitable for this high power application. So let's discuss about the silicon carbide device. I'm not going into GaN device because these are not used in a railway application. So this again, this silicon carbide device is commercial applications, like different commercial applications it is used. This PFC, motor drives, UPS, like said, sorry. Central inverters, then automotive industry, military applications. So wherever the high power is required, so there silicon carbide device is used. So now the advantages of the silicon device, it is having high voltage. This electric field intensity is 10 times than that of the silicon, and then high current carrying capability, which is 4 times than that of the silicon. And then high temperature operation capability. So that this device based converters can operate properly in 300 degrees Celsius. So if any of you are working with the silicon based device, it may not it is even at 100 degrees Celsius, it will not operate properly. So then like even if the temperature increase to 300 degrees Celsius, still the converter properties will not change with respect to the device. So then losses with respect, switching losses are much lower, and then conduction losses are also much lower than that of the silicon device. The properties, if you see the silicon device which is compared here with respect to silicon, so band gap is approximately 3 times than that of the silicon. And then with respect to energy gap, breakdown field, thermal conductivity, everywhere this device is much better than that of the silicon device. So now the silicon carbide device, like commercially there are like all the devices are available which are like based on the silicon carbide material. So these are like diodes, different switches, IGBTs and all, everything is available for this particular power device. So the structural point of view, if you see here, so the structural point of view, the silicon MOSFET and silicon carbide device here it is shown. So with respect to silicon MOSFET, the size of the device it reduced to 110 times. So basically, due to the electric field, the size of the device, basically silicon device is 10 times than that of the silicon carbide device. So size of the overall system, if the device is reducing the size, and if it can operate at high frequency, then all the magnetic component size will also reduce. So the overall system size will reduce. So then the overall system, the converter size will reduce. Okay. So with respect to the cost, you can see here. So basically, silicon power conversion system, if it is the round, if it is shown the whole overall cost. So the blue portion here in the left side, it is shown the losses. So basically, cost of the silicon device. In the right side, the silicon carbide power converter system. So basically, blue one, which is like much bigger than that of the silicon. So this is the silicon carbide cost, which is actually much higher side than the silicon, because silicon is the kind of mature technology. Silicon carbide is the new technology. It needs some more time in order to reduce the cost. So the cost is much higher than that of the silicon device. Even the cost is much higher than the silicon device. Still, the overall system, if you see the gray portion, it is the savings in the cost. So the still, even if the silicon carbide is much more expensive, from the overall system perspective, there will be reduction in the cost, because magnetics and the other component size will reduce. So then what will happen, we will have cost benefit in that system. Also the heat sink size will reduce down. So manufacturer of silicon carbide, so basically there are different components. So means like IGBT, BJT, MOSFET. Based on that, like there are different manufacturer from where these devices can be purchased. So Cree has like I think 20 kilovolt devices. So the high voltage this silicon carbide device IGBT. So they can you can, if you are looking for, so then you can actually see their website. So there are other manufacturer also like Fairchild, Mitsubishi, Philips, and the Infineon, Hitachi, and all these companies from where these devices can be procured. So this silicon carbide based power converter for traction. So if you see the size, so basically the left side is the silicon based silicon IGBT based like system, so which is having 6.5 kilovolt and 25 ampere rating. So this is used in traction application, and the right side is the silicon carbide device. So basically that is 15 kilovolt and 10 ampere silicon carbide MOSFET, which is used in the traction system. So you can see the size difference from here also. So it is actually these devices are connected to heatsink here. And then silicon carbide based power converters, which are used in the traction for high frequency. It's like here it is medium frequency transformer prototype is given. So basically here the few kilohertz, basically less than 10 kilohertz. So first is the 500 kilowatt 8 kilohertz system, and then hollow aluminum winding. This medium frequency transformer is given in B, and then C is the 166 kilovolt 20 kilohertz, and then D is the 65 kilowatt 8 kilohertz. So these are the different high power medium frequency transformer prototype, which are developed due to the development of the silicon carbide device. So before that, if you have seen, if you remember, so these are like different material. If you see here, so this B, it is the aluminum hollow aluminum winding for this medium frequency transformer is used. So the different nanocrystalline material is used for this transformer. If you remember the transformer which I have shown you earlier for 1 kilohertz and 5 kilohertz, there the material was different. So that is again like due to the development of this high frequency device, development of this core material is happening, and that is allowing for the system to operate at a high frequency and high power level. So now the challenges and opportunities. So having said that, wide bandgap devices and then different converter topologies which will enable the operation of this railway traction much easier. But like again, like this will not come so easily. There will be lots of challenges. So as you see, the issues such as that operating frequency and the number of cascaded module optimization, and that too like implementing soft switching, implementing control method, and system reliability should be also need to investigate. So those things are will be very, very much challenging. Means operating at high frequency, even the cascaded module will be challenging issue. Even if the system is operating at lower frequency in 1 kilohertz, if we try to operate at 100 kilohertz, so then what will happen, there will be other non-important thing in low frequency that will become quite significant in high frequency. Means the parasitic parameters. So maybe like the small parasitic capacitance inductance becomes quite high in the high frequency. So we need to see that how to take care of those issues, how to design the converter. And then again, like controlling the converter at high frequency, there will be many challenges related to EMI. So if you see that in low frequency, EMI EMC problems are not that much, but at high frequency those problems will become quite significant. Then we have to see the filter for that. and the system reliability. So if there is like if it is operating at high frequency, any small like fault, or maybe any small uh, like harmonics which are of like higher value, high frequency harmonics, so which are not significant in low frequency, but that may become significant in high frequency operation. So those things how to minimize, and then how to like optimize the system reliability, that part need to look into. Also the like fault operation, so basically how to protect the system from fault. So low frequency system, because the frequency is low, if the fault is there for some time with respect to that frequency, it may not affect the low frequency system. But if the fault is there for like some, like whatever prescribed limit is given in power system, so in that time, so in high frequency system that may become significant. So then again we have to see that how to take care of that. There are several issues, they may become like affect each other with respect to one this fault or other things. So those things need to be investigated. Also like now the silicon carbide, whatever like device property is shown, that is the component level properties. Again in system level, how these devices will react in the, like if we try to operate at a very high temperature in the high power high frequency level, how this property of the devices will change, that also need to be investigated. So there will be many challenges. So it's not just the device, since it is like available for high power, we can directly replace the thyristor or IGBT based system using those devices. It is not possible. So using those devices will be very challenging. Those like properties benefits of these devices will come with lots of challenges, like designing driver, like replacing the overall system, the converter topology, all these things will be like kind of challenge, and also opportunities for the researcher need to look into for these high power applications. So now the conclusion is that despite the wide bandgap devices are expensive and also difficult to handle, but and also like difficult to get, at least in India it is very difficult to get, we need to import from outside. So but like in near future it will become available, then it will be much more easily then we can access it much more easily, and also the price will reduce down. And the power electronics transformer based systems can operate at high frequency and have probably simpler structure, and then which will probably withstand much higher catenary voltage. And the probably overall system will have smaller size and higher efficiency for this traction application. So these are the different references which I have used. Yeah. With this, thank you very much. So if you have any questions, you can ask now. Hello, can you hear me? Hello.
Yes, ma'am. Yes, ma'am. Yeah, so now open to questions.
Hello, ma'am.
Hi, hello.
I have some questions.
Yes.
Comparing this wide gap devices to normal silicon-based IGBT, what do you feel that the EMI issues will be more, because what literature has shown that the gap devices will have more EMI issues. So don't you think the cost will further increase because because we will requiring the extra filters? Or are there any techniques to reduce those EMI issues without the needing of extra filters?
See, the thing is that again, we cannot get all the benefits, so there will be challenges. So even like when we move from line frequency transformer to medium frequency transformer, there were challenges. And again, those challenges needed. I mean, we using the power electronics converter, people solved it, and then we found the advantages, like overall advantages. Yeah, there will be challenges. Operating any converter at high frequency with respect to line frequency or the lower frequency level, that is very challenging job. EMI issue will be very high. I mean that problem will be there. Again, that is also one important area for this wideband gap devices people are working on. So this EMI filter, how to design EMI filter for this high frequency high power converters. This is there are different methods people are following for this EMI. So there are like different kind of EMI, conductive, radiative, this kind of EMI. So the conductive kind of EMI, so that can be reduced down by using filter. So again, as I'm saying, so if you see, like so there are EMI standards which are available if we want to use any system in application level. So that EMI standard need to achieve. So then, that EMI test need to be done. So in that, what happens? So like if our system is operating at higher frequency, let's say 100 kilohertz, so that EMI frequency will also be higher. So then the filter size which are required for these converters, so that is required, that you have to use, but the sizes will be much lower. And as I am saying, so if you see the cost of the overall system, so if you see, let's say um, any converter, let's say this converter, so there are different modules present, right? If you see here, there are like n number of modules. So if it is possible to replace n number of modules by like one or two modules, so in that sense probably we are simplifying the overall system, and then we will have benefit in that. Means even though we will be using more complicated system by considering filter, and also like we have to design it complicated in the sense, not in terms of the converter topology, in terms of like designing the system. Means the probably one H bridge will be there, so designing one H bridge will not be difficult, but associate parameters, let's say input EMI filter will be there, and then again the layout need to be designed properly so that there is no extra line which may cause like additional path for this high frequency operation. So these kind of things will be there. So that is why overall cost will reduce down, even if the device cost is very high at this moment. Still, the overall cost will reduce down, because magnetics plays very important role. If we go from like low frequency to high frequency, in your filter, what are the parameters will be there? Capacitors and inductors. Inductor size you are reducing. So if you see, just for an example I'm telling you, like inductor means what, like there will be core, and then around it there will be wire which you can wind. So now there are, so if you're interested, you can see there are like hollow core, means like air core people are using at higher frequency, means megahertz level. Means in that level inductor value is so less, the core requirement is not there. So because filter means there will be low power, right, very low power, so like the filter will be like lower value, so then the frequency will be much higher, so only the wires may be sufficient in that level, so whatever is required for this EMI. So yeah, these are again like kind of area people are working on for this high power high frequency application. Is it clear, or do you have?
Yes, ma'am. But when you are saying that you will replace these number of modules by a single module at that power level, then again there will be a lot of issues or challenges are there, like skin effect will be there, proximity effect will be there, and heating of the transformer will be there. Then cooling requirement will be more.
That is the transformer I told you, na. So this challenges again like this insulation related. So whatever like where we have, so that again like kind of area people need to see the where insulation in that frequency level, is it suitable, or people need to look for different material like insulating material, and like in the cooling method need to be used. So this again like those all are challenges. So see, the new device comes up with new challenges and new opportunities. Opportunities we can see, but challenges we have to solve.
Also, if you replace the modules with a single module, I think the reliability will be less in a single module, as because as you are saying that it will have simpler structure. But if any of the device of that edge bridge fail, then whole system will stop working. Whereas you can easily replace or bypass one of the modules which are there and can still work.
So yeah, so those are again challenges with respect to, if you see here, the system topologies, how the topology should be. So the reliability can be maintained for that kind of operation. Again, I'll tell you one thing just to answer your question. So if you see here, like the silicon based system, so the converters are connected in series, these modules. Even if any module fail, the system will not operate. It is not connected in parallel. So again, you have to replace, then only the system will work. And again,
We
like,
can
hello.
can we not bypass by using relay those modules?
So that again comes into like the system, how it is developed. See, if it is like this kind of system, and if it is delivering certain power, bypassing that thing will not deliver that much power, right?
Yeah. Partial power, or we can keep the redundant module as well.
That way, like, you have to see, you, I mean, as you are saying that fault, there will be method to check fault in which system it is there. Obviously that system will be replaced, so that the system will operate properly. Again, like, replacing as it is coming, so that will be easier in like single module. Again, it will be like in multiple module, then again, like, there will be different reliability issues. More number of converter, if it is there, then more number of switches will be there. Then the more number of switches, more number of capacitor, again that reliability issues will come. So this reliability issues in the line frequency, basically medium frequency transformer, will have different aspect with respect to high frequency. High frequency will have simpler structure. It will be simple, easy to find out. Again, will be like kind of we have to again see, the thing is that now we are thinking straight. We are thinking that this H bridge here we can directly replace with silicon carbide and that will operate. But we have to see that how the system topology will work using this silicon carbide converter. So this is in research level, like, people are thinking that okay fine, this will work properly, but still in that level, in the application side, in simulation and all, it will be easy to implement, but actual system how it will operate, that need to be tested, and then only it can be understood. Those challenges, whatever you are saying, it will be there. We
Yeah,
need to
and one more doubt I'm having. So during the presentation, you have also mentioned that the capacitors will have lower reliability. So what makes the capacitor more vulnerable? Are there the ripples on the capacitor or charging discharging cycles?
So there are different capacitor material. There are like electrolytic, ceramic. Then there are other material also. Have you heard of all this material?
Film capacitors I have heard
Film
having high
capacitor, right? So these are film capacitor. Now it is very expensive and not available for very high voltages, right? So now this electrolytic capacitor. So these are generally used. You will see it everywhere. So now this electrolytic capacitor, these capacitors are not reliable. Reliable means what? After few years, like in a span of few years, you need to replace those capacitors in the converter. So these capacitors, as you can see, the material, with respect to material, this capacitor doesn't behave properly, and this capacitor need to be replaced. So with respect to capacitor reliability also, there are like different work available. So how many years one capacitor can work properly? So if you see the battery, like, you have heard of battery now, that like lifetime of battery will reduce, or the device, even the device, silicon device, after like few cycle, not few, I can say like thousands of cycle, the device property will change. Similarly, the capacitor. So as you can see, the film capacitor is having better reliability than the electrolytic capacitor. So, but it is not available for high voltage, and also it is very expensive. So if it is possible to, so there will be, so if you try to see different literature, so there are literature capacitor less converter. So wherever it is possible to replace the capacitor, if you can replace, the system reliability will increase. because the capacitor property will change after a few years. So they may not work properly as you have like started working with.
So same thing can be said regarding the inductor as well.
Inductor, until and unless it is like if you are operating it within the safe zone, then it is okay. If it is going into saturation level, then the properties will change. You know, hysteresis band. So that so there you have to see that how this, but inductor is not as vulnerable as capacitor. So capacitor is like kind of the parameter which will cause the reliability issue in the system.
So, but if you compare the sizes of inductor and capacitor for the same power, I think the capacitor will require the smaller size. So wouldn't that will increase the power density?
Capacitor will not have any effect with respect to the frequency. So if you try to see the size of the capacitor, like that depends on the ripple, right? Current ripple it is taking. The frequency part is coming when basically if you try to see any converter, na, buck converter, boost converter, inductor is the parameter which is processing the power. So basically ripple it is taking, and then it is actually so whatever will be the switching frequency, inductor frequency will be that much. But capacitor where it is coming, so in order to like output side, in order to maintain the constant DC voltage for DC to DC converter, or so if you see this here, generally what happens that after diode bridge there will be a huge capacitor, electrolytic capacitor, so that will provide the DC constant output. It will take the ripple, high frequency ripple, right? So then capacitor is not coming into picture when the power is basically switching. So any switch, if you see any switch when it is like turning on and turning off, generally what happens, the inductor charges and discharges and process the power. So if you increase the frequency, let's say in conventional boost converter also, the inductor size will reduce, but the capacitor size will remain same. So capacitor size will not change with respect to the frequency until and unless you change the converter type. So generally what happens that PFC application, if you see power factor correction application, so let's say input frequency is around 50 hertz. So output is DC. So then what is happening, the capacitor output will have like 100 hertz frequency ripple. So that ripple will remain 100 hertz even if you change your converter operation from 10 kilohertz to 100 kilohertz.
But if you change the reference frequency, then also because then the
Reference
ripple.
frequency means like PFC means what? It will be connected to some line 50 hertz or 60 hertz, right?
Yeah, but in medium frequency transformer, the front end
No,
will
no,
be
this is I'm telling the power factor correction. So it is
okay.
not
Okay.
medium frequency transformer, it is coming. So again, like medium frequency, again the reference will change there. So the capacitor, like again, if you see here, the capacitor is not generally connected like here with respect to the, let's say inverter output will be connected to the motor. Their capacitor is not connected. So before inverter it is connected, where the DC to DC output is coming.
Okay.
Right.
Okay.
So that way, like you have to see. So that can be that size will reduce down, no, by using different converter prototype, by using active filter, passive filter, all these methods, but not changing the frequency of operation. The main parameter. So if you see any system, the with respect to capacitor, the magnetic size is much more higher. Everywhere you will see this transformer, when I am saying this line frequency transformer here or the medium frequency transformer, here the transformer is the one which is basically handling this frequency, this line frequency or the medium frequency, right? In the converter, inside this AC to AC converter, anywhere do you see the capacitor which is coming into picture? Because the magnetics is the part which is actually impacting the size, basically increasing the size or reducing the size depending upon the frequency of operation. Okay, is it clear?
Yes, 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 ma'am. Thank you so much.
Okay, okay. Any other questions?
Yeah, any other questions to ask for participants? Nobody written in chat also.
So there is no other question.
Yes, ma'am. Yes, ma'am. Yeah. So
Okay then. Thank you very much.
thank you so much, ma'am, for detailed talk and answering the technical questions.
Thank you very much.
With that note, I would like to give you the virtual token of appreciation, ma'am, for your talk. Actually, kindly accept it. Hope you can able to see it. So,
Thank you very much.
Yeah,
Thanks a
thank you,
lot.
thank you,
Thank
thank
you
you,
for attending my presentation. Thank you. Okay. Bye.
Thank you, ma'am. Thank you.
thank you.
Okay, so participants will meet again at 2:15 p.m. for the second session of the day.
Okay, yeah.
Okay. Thank
Thank
you
you.
all. Thank you all.